In this lesson, we're going to talk about parametric surfaces, and we'll start with a relatively simple one. The plane 3x plus 2y plus z equals 6. And we know what that looks like. In the x direction, if y and z are 0, x would go out to 2. If x and z are 0, 2y is 6, y would go to 3. And in the z direction, if x and y are 0, z is up at 6. So again, we have a plane, but it's going to go through these 3 points. Well, I want to express this parametrically. So what do I mean by that? Well, I'm going to start with a point UV. I'm going to use some function R that is going to send it to a point X, Y, Z. So the simplest way to do this here is to simply let X equal U, Y equal V. Then Z would just be 6 minus 3U minus 2V, because of course Z is 6 minus 3X minus 2Y. So Z is 6 minus 3U minus 2V. So the way we're going to write this using this notation, R of U comma V is U comma V comma 6 minus 3U minus 2V. This is how we're going to express this as a parametric surface. So let's take a look at the graph to see what it looks like. Our domain for U will be negative infinity less equal U less equal positive infinity, or equal I guess we don't need. Similarly, V will be from negative infinity less than V less than infinity. So basically, U and V could be anything. So again, let's graph. So here's how I input that. X of UV is U, Y of UV is V, Z is 6 minus 3U minus 2V. Choose ranges of values that will give you a decent looking graph. So I've chosen these. As I graph it, do we see indeed it looks like X probably goes out to 2, Y probably goes out to 3, and Z goes up to 6. So that looks reasonable to me. So that's a representation in parametric form for that plane. So again, we're considering moving from a point UV to a point XYZ on the surface. Now let's take a look at another sort of surface. So I've got x squared plus y squared plus z squared equals 9, which we recognize is a sphere of radius 3. Now, if you want to try to approach this the same way we did the last problem, you will fail, because if z is a function of x and y, it can't get both the upper half and lower half of the sphere. As we'll see here, z squared is 9 minus x squared minus y squared. I can get the top half. Z is the square root of 9 minus x squared minus y squared. So I could say x is u, y is v, and z is the square root of 9 minus u squared minus v squared. But that's only going to get me the upper half of the sphere. So using r of u comma v notation, we're going to get u comma v times the square root of 9 minus u squared minus v squared. And looking at our picture here, the x's would range from -3 to 3. So -3 less equal u less equal +3. Similarly, -3 less equal v less equal +3. So let's go ahead and look at that graph and see what it looks like. So again, x is u, y is v, z is square root of 9 minus u squared minus v squared. U and v both going -3 to 3, and we get this graph, which is not terribly appealing because I only get half of the graph, and then we have this noise that is happening on the xy plane. So is there another way we can do this? So we've done our first parameterization, but there is another way we can do this, namely remembering how spherical coordinates work. So x is rho sine phi cos theta. Y is rho sine phi sine theta. And Z is rho cos phi. Well, we know that in this example, we know that the radius is 3. We have that fact. The radius of the sphere is 3. So rho is 3. So I get x is 3 sine phi cos theta. I get y is 3 sine phi sine theta. And we get z is 3 cos phi. Now remember, we're going to go from a point uv to a point xyz. So uv gets moved to a point xyz. So how are we going to do this? Well, let's say u is going to be represented by phi. So wherever we see phi, we'll call that u. And whenever we see theta, we'll call that v. Now we know phi ranges from 0 to pi, north to south pole. So 0 less equal phi less equal pi. So they'll give me 0 less equal u. Similarly, theta goes from 0 to 2 pi, 0 less equal theta less equal 2 pi. So 0 less equal v less equal 2 pi. So let's put this together and rewrite this thing as a function of u and v. So just replacing the phi and the theta with u and v, we get these three versions for x, y, and z. So now let's go ahead and construct that function r of u comma v, which in the x slot 3 sine u cos v, and the y slot 3 sine u sine v, and in the z slot 3 cos u. So let's look at this graph. So x is 3 sine u cos v, y is 3 sine u sine v, and z is 3 cos u. And what else are we going to say here? U is our phi, goes from 0 to pi, north to south pole. V is our theta, goes 0 to 2 pi, goes all the way around. Now, is this a better graph? Is this a better representation of that sphere? Sure it is. We get the entire sphere. It's nice and smooth. The way the computer is drawing it is much more appealing. So that would be our preferred representation for that sphere. So spherical coordinates would be the preferred representation to describe that in a parametric form. And next, what I'm going to look at is surface of revolution. So let's take a look at y equals the square root of x on the interval from 0 to 4, rotated about the x-axis. Looking at our 2D representation, we get this. And this is the point. X is 4, y is 2. We're going to wrap this around the x-axis. Now, how do we perceive this? Can we imagine what this is going to look like? So we see we have the mirror image down here. And if I fix a value x, what we get here is we get a circle. Now, on that circle, the x values are always the same. So the x values aren't changing there. So for this red circle, the radius of that red circle is what? The radius of that red circle is the y value, which in our case here is f of x. So the radius is f of x. The x values are always the same. So I have a circle. That red circle is going to be defined by that radius. This is the x direction. This is the y, and the third direction here is z. So this is not our typical orientation, but we can see that this red circle is in the yz plane. So in the yz plane, what are we going to have? We are leaving x alone. X is not changing on the red circle. Then I have a radius of f of x. So I could say f of x cosine theta Then I could say f of x sine theta will give me this. Well, let's go ahead and let x equal u and let theta equal v. So if x is u and let v be theta, and then what would f of x be? Remember we said f of x is the square root of x here. So in my example, f of x is the square root of x, which would be the same thing as the square root of u. So if I'm writing this as r of u comma v, again, if I'm wrapping around the x-axis, x is not changing on that red circle. So that's just going to be u. That's not changing. I have a circle in the yz plane with radius f of x, or if you like, square root of u cos v, and then square root of u sine v. Now, what do I want u to range from? What makes sense here? Well, looking at my picture, I'm going from 0 to 4. So 0 less equal u less equal 4. And for my v is creating that circle. So 0 less equal v less equal 2 pi. So let's look at the graph. So here's how I have it defined. X is u, y is square root of u cos v, z is square root of u sine v. U from 0 to 4 and v from 0 to 2 pi. What does that look like? Okay, might be helpful to look at it in the two dimensions. Remember, y equals the square root of x is how we define this. Y is the square root of x, again, rotated around the x-axis. We see what that looks like. And then there's our 3D representation of that surface of revolution. Next, I want to look at y equals 2x on the interval from 0 to 3, rotated around the y-axis. So this is our image. Again, I'm calling this the x-axis. This time I'm calling this the y-axis just to enable me to visualize it this time. Well, once I'm here, you'll notice on the red circle, the y value is constant, so y is not changing. So y is unchanged. We have a circle that is in the xz plane. Remember, z is coming out this way this time. So the circle is an xz. And what is the radius of that circle? The radius is the x value. So let's do some analysis here and determine what that's going to be. Well, we see y equals 2x. So y divided by 2 is x. So my radius equals y divided by 2. So again, y is unchanged. So if I have x equals, I have y equals, I have z equals. Y is unchanged. I'll just call it y for now. The radius is y over 2, so I will say y over 2 cosine whatever theta, and I will say here y over 2 sine theta to go ahead and get that. And then let's replace what? Let's replace y with u and theta with v. So y will be replaced with u and theta will be replaced with v. What is that going to give me? X is u over 2 cos v. Y is u, and z is u over 2 sine v. So let's go ahead and write this in r of u comma v form. R of u comma v is in the x slot, u over 2 cosine v, comma u over 2 sine v. So this will be my parametric representation for this surface of revolution. Let's take a look at the graph. Note, if x goes from 0 to 3 and y is 2x, y is going from 0 to 6. 0 less equal y less equal 6. And theta, of course, is between 0 and 2 pi. So that will tell me that u is between 0 and 6. 0 less equal u less equal 6. And v is between 0 and 2 pi. 0 less equal v less equal 2 pi. So here we go. X is u over 2 cos v. Y is u. Z is u over 2 sine v. U from 0 to 6. And v from 0 to 2 pi. Take a look at our graph. What do we think about that? I guess that looks pretty good. Take a look at our two-dimensional version. Can we believe that's y equals 2x? Maybe I can zoom it a little bit to see it just goes up to 6. Go back to our 3D version. Again, you can see y goes up to 6. X goes from 0 to 3. So just keep in mind, when we're doing our parameterizations, you want to use the most reasonable one. Make sure you're defining it carefully and watch your range of values.